Welcome to another lecture in this series where we have been learning about the fundamentals for embedded systems. In the last lecture, we learned about the operational amplifiers. In short, we call them op-amps. Specifically, we learned about the two main applications of op-amps. One was to do the amplification of the input, and then the second one was to do the mathematical operations, such as we can use op-amps for doing differentiation, integration, summation, division, difference, so forth and so on. One thing that was common amongst these two applications that we have learned was that we were using op-amps in the closed loop configurations, such as shown here. So in the closed loop configuration, we have a feedback that goes from the output to the input. Today we are going to learn about another application of op-amp, but we're going to use the op-amp in the open loop configuration. So let's take a look at what we call a comparator. Once again, the open loop configuration of op-amp looks like this. There is no feedback that goes from the output to the input. This is really what a comparator looks like. It's pretty simple. Before we understand how this comparator works, let's take a look at some use cases. So let's say we have a battery and we want to know when the battery voltage drops below a certain threshold. So on the x-axis I have time, and on the y-axis I have the battery voltage, and over time, let's say this is how the battery voltage drops, and I want to know when the battery voltage drop is below a threshold which we call V reference. So for use case like this, we can use a comparator. So we have two things. We have the V that's varying and we have the fixed reference. Here we have a comparator. Again, we have two inputs that we can attach something to. We can fix this input V minus to V reference. So this will be a fixed. And V plus, which is the non-inverting terminal, let's say we supply the V in, which is varying. According to what we have learned in the previous lecture, we know that for the open loop configuration op-amp, the gain can be on the order of 100,000. So if we take that number and let's say the gain that is possible from here is 100,000, then V out is simply going to be equal to gain times the difference in the input. So V in minus V reference. That means if the gain is 100,000 and V in is varying, if I fix this V reference to 0 just for simplicity, let's say this is 0, then V out is simply equal to whatever gain is theoretically possible from here times the V in. Now if let's say the V in is a sine wave and it goes from +1 to -1, so that's the range. So then if let's say this is +1, that's the maximum on the positive side, then according to this equation, V out would be plus 100,000. And if this is -1, then it would be V out minus 100,000. And then also in between, anything in between +1, -1 would be whatever in between that. But this is wrong. This is not what the op-amp is going to give us. Why? Because op-amp is limited by whatever power supply is powering that op-amp. So if let's say the power supply is +10, so we have a dual power supply, and here -10 volt, the maximum gain that's possible from this op-amp is +10 on the positive side and -10 on the negative side. So we need to really understand this. And this region where you are pushing the limits, this is called op-amp being in saturation. That means when you have the input as +1, so even though theoretically this is what the max is possible, but this is not true. So output when you have input as +1 is going to be +10 volt, and when you have output input as -1, you have -10 volt. So what happens in between? So if the input is between -1 and +1, what happens? Take a pause. I'll give you the answer. So the answer is still going to be +10 and -10. Why? Because the math says that your output should be 100,000. So no matter whether it's +1 or plus 0.00009, whatever, it is still going to be a big number. That means we are going to be hitting the limits. So it's going to be capped at this number. So if we have an input that looks like a sine wave, you can imagine that the output of this is going to be a square wave. Maybe I'll draw it on the same graph. So the output is going to be a square wave, and the limits of that would be +10, -10. This is the output. Now, how can we use this as a comparator? So if we fix the V reference, so if V reference, like here I fixed it as 0, so let's say this is my V reference. So I can know by looking at the output that when my output of the op amp is plus whatever the power supply is, I know that I'm above the threshold, which is 0 in this case. And when my output here is equal to minus the power supply, whatever the power supply here is, -10, then I know I'm below the threshold. So that's how we use a comparator in order to compare the input voltage to some fixed threshold. This is pretty simple. And one thing that you can learn beyond this is a Schmidt-Traeger circuit. So one thing to note here is, even though the math works out and everything, it gives us what we want, but in reality the input signals are not as clean. So the input signal can look a little bit jittery. So it would look something like this, like that, like that. So when that's the case, if you define a fixed reference, the sensitivity would be pretty high, because anytime it goes slightly below above the jitter and slightly below the jitter, you will have a different output, and that's not practically true. So for those cases, we define some hysteresis. So rather than defining just one threshold, we define two thresholds with some hysteresis, and we can use what we call a Schmidt-Traeger circuit. I'm not going to cover that in this lecture today, but if you want me to expand upon what Schmidt-Traeger circuit is, let me know in the comments below and we can cover that in a separate lecture. I'll stop here. So just to summarize, what we have learned in this lecture and in the past lecture is about the op amps. We know how op amps can be used in open loop configuration, in the closed loop configuration, and we know the op amps can do the amplification, they can do some mathematical operations, and now we've just seen that we can use them as comparators. So that's all for the op amps, and we'll stop here. In the next lecture, we'll move on to a new topic. So I'll see you in the next video. Thank you. Bye.